Okay, welcome everybody to part 2 of generative adversarial networks. Oh, do we have the clicker today, or is that somewhere else? Sorry about that. Just plug it in there. Okay, so for part 2 of generative adversarial networks, we're going to start with just a little bit of a recap and an overview of what we talked about last time. So last week we just introduced GANs, what makes them unique, what they are, what you can do with them. And this week we're going to talk in a little more detail about how they actually work, how we optimize them, and all of their optimization issues. Yes, question? Yeah, it doesn't line up perfectly when I use this, but it'll. Yeah, I'm gonna have to keep adjusting it manually, and then he's got a separate version on the stream, but this I'll have to do for now. So anyways, just a recap of what we did last week, an opportunity for any questions there. We started with the difference between generative and discriminative networks. Discriminative networks are the types of things you guys have been dealing with traditionally. You have some inputs like images or audio, and you have some labels like what class is it, what image is in, what type of item is in this image, what's the phoneme, things like that. Our generative networks are when we flip the distributions, we're trying to find things like just producing images, or given labels produce images. So things like P of X given Y, P of X and Y. Those types of notations are when we're talking about generative networks, versus discriminative networks would be P of Y given X. Just a quick recap on VAEs, which are now, I guess, 2 weeks ago, but still relevant because we're going to compare them with GANs. VAEs are similar to autoencoders. They have an encoder part and a decoder part. That's P of Z given X and P of X given Z. And that allows you to transform from your input space to what we call the latent space, or the encoding, depending on who you ask. Normally something like a Z is what we use. And it allows you to then transform back. So the encoder and decoder is a pair. That Z is not something that you give it. The Z is something that is inferred. It's something that's learned. This is true of all autoencoders, not just variational autoencoders. What makes VAEs different is that you have this regularization term. There are many ways to view it, but that's probably the simplest way. There's a regularization term that's saying this Z that you're learning, that you're inferring, that you're coming up with yourself should look like a Gaussian, or whatever you want to call your prior. So you give it some prior and you say, learn your encoding, but the marginal distribution of this encoding should be X, Y, Z, whatever you give it. Traditionally, Gaussian's the easiest. So we end up with something at the bottom. You see the negative log likelihood term on the left. That's traditionally called your reconstruction error, something like that. And then you have this KL term. So basically, it's 2 parts to your loss. You have try to reconstruct your input as well as you can, while at the same time making sure your encoded distribution looks like a Gaussian. And that's how to interpret those 2 terms. And now we come to GANs. GANs are relatively new, flurry of activity. Everything we're seeing in the last 2 weeks has been from like 2014 through 2018. There are a couple very recent papers in here. And it's still a very active area of research, and we'll go through kind of how it's evolving and changing. But in some ways, that does make it different than a lot of the lectures you're used to, where we just give you, maybe a little bit of history, but here's the answer, we figured it out, and here's why it works. This is much more consensus, and here's where the literature is now, and here's kind of what people are working on, and the new ideas that have all started surfacing, and how we think they can turn into something even better. But it's still ongoing, so keep that in mind. GANs are a new way to build these generative models. VAEs are also a generative model. But GANs have more flexibility. They have more potential in terms of actual results. They're much cleaner in terms of theory. It's way more complex, so there's all types of things that people are digging into. So here's our overall diagram of a GAN. We went through this kind of at length last time, but now is your chance to ask any questions about what these parts are. So basically, you have random noise goes into a generator, and that generates your image. And then you have a training set. Your discriminator tries to tell what the difference between the 2 distributions is. And your fake image and your generator tries to beat that discriminator. So the generator never gets to see your training set. The way that your generator matches your training set is through the discriminator, which tells it what the difference is. Slightly more complicated version. This is the notation we went through last time. Here we have your standard function at the top. That is your min-max gain. That's what you're trying to min-max. And then we have, with notationally, what we just said, but as written in our probabilistic notation that we tend to use. And then our final diagram is the fun one, which we went through, and we're showing that we have real data, and we have some generator who doesn't get to see anything. That's why he has a blindfold. He gets some input distribution, and you've got someone that's telling what the difference is. And each time he tells what the difference is, the generator tries to do a little bit better, and eventually the forger gets to forge something that looks just like the real data. So also you can check out that post. That post is called a GAN in 50 lines of PyTorch or something like that. So if you're looking to explore it in PyTorch, it's very simple GAN, but it's worth looking into. So with that, that kind of brings to why are we doing GANs? What are the implications? What does all this mean? Why are we doing it? The metric that we're using to say that this image is similar or dissimilar than another image, that metric is now a neural network. It's not an L1 distance. It's not an earth mover distance. It's no preconceived distance that we've written for comparing different images. It's something that's natural, that's arisen through a neural network. What that means is that neural network, that loss, can actually start to be something you call perceptual distance. As we talked about last time, if our brain is neurons, et cetera, you can kind of think of GANs and a discriminator as having the potential to represent the complexity of metrics that we as humans kind of represent. When you say an image is similar to another image, you're not saying that the mean values are the same. You're not saying the pixels align correctly. You're saying the content of this image is similar to the content of this image. How do we represent content these days? Through a neural network. So if you want to have something that tells you if two images are similar, what you really should be looking at is a neural network's outputs, not just L1 or something simple like that. And what this also means is that all of our biases that we've built into networks are now a part of our loss function. Since we're building a generator and we're training it through a discriminator, if that discriminator is shift invariant, then that means that our loss function is now shift invariant. So we have something that can compare two images, but doesn't care about slight shifts. And you compare that to a traditional loss like L2 or L1, which means you take each pixel value, you line it up, and you compare the distance pixel by pixel. Slight shifts give you completely different values. So this kind of gives you a sense of why GANs are so fascinating, why they're so powerful. We can start talking about new things like perceptual distance. We can start generating data in this real interesting naturalistic way. And that's kind of why it's fascinated people. And this is the good side of GANs, which is what we started with last week. So with that, we'll see if you guys have any. Oh, actually, one quick slide about the kind of comparisons between them. VAEs are guaranteed to converge, obviously with some basic assumptions, but with some minor assumptions, your VAE will get to a stable point. It might be a little blurry, but it will get there pretty much no matter what you do to your hyperparameters, within reason. GANs, you do something wrong, you can get chaos, you can get mode collapse, you can get all types of situations where GANs just don't give you remotely close to what you're looking for. But on the flip side, GANs can do all of these additional things. They tend to generate sharper images. So when GANs do work, they're much harder to train, but when you do train them correctly, the results are like astounding. That's kind of why we see this duality where some people are kind of completely sold by GANs and other people are like, I don't even know if that's going to work at all. It's a trick. So there's a lot of discussion that it's been generating. Also last week, we talked about what we can do with GANs. So this is taking us up through what the core GAN framework is. And now we talked about what kinds of ways you can work that core framework into more complex models. So your core GAN is just generating your input data. So you give it a bunch of images, it gives you out a bunch of images. All of these are more complicated versions, like you give it labels, it gives you images that look like those labels. or you use a GAN to, and that's the first example, conditional GAN. Or there's a categorical GAN, which allows you to do clustering based on GANs. There are BiGANs, which allow you to train encoders and decoders. So we're not going to spend a whole lot of time on these guys. We did talk about them last week, but if anyone has questions about up to here, because I think that's about what we covered last week. So any questions so far, or anyone wants me to go back through any of the architectures we covered before? All good? Okay, great. Just shout out if you do have questions, by the way. I know I'm kind of breezing through this to get to this week's content. So the story so far sounds great. What's the problem? The current major problem is just optimization issues. There are some other problems, but that seems to be where the story kind of falls apart. And the question is, why are they so different than your traditional networks, your feed-forwards that you do every day? GAN optimization is different because gradient descent is very standard. Everyone knows what gradient descent is. There are a couple optimizers. Yeah, some people do some research on optimizers, but in general, they do about the same thing with, a couple tweaks here and there to momentum. Loss functions, yeah, there's like categorical cross entropy, and then some people like to do like a hinge loss type thing. There are, 3 or 4 choices, some slight variations people will do. But a lot of the research in these feed-forward networks has just been on individual modules, dropout, batch norm, that kind of research. GANs, on the flip side, have opened up this kind of new area of research where people are actually studying new optimization strategies, new optimizers, new losses. Like, how do we actually understand what optimization is? And that's because GANs are multiplayer optimization, which is more a general case of the situation where everything you've been doing so far is single-player optimization. So you can think of everything you've been doing so far as like the one-player version, and suddenly we're in 2 players and everything kind of goes haywire. But it's a much more complicated world that we're in once we start dealing with multiple dynamic elements. So in terms of GANs and why we have these kind of optimization issues, there are a lot of theories. As we said, not everything's fully worked out, but there are a lot of reasons why you could imagine why GANs are not going to train as well as, straightforward cross entropy, put MNIST digits in and get labels out, that kind of thing. So one fundamental reason is 2-player games just don't converge using gradient descent. This is more when you start reading about Nash equilibria and how they work. Like, not every single game that people play has an equilibrium that it will reach. And even if it has an equilibrium, that doesn't mean that it's going to hit it at any time soon. Please. Right, exactly. So when you really get into GAN research, there are kind of 2 branches. One branch is more the stuff we talked about last week, which is, hey, I used a GAN to make really sharp images. Or like, hey, I used a GAN to generate some audio or text or whatever it is. And then there's the type of GAN paper, which is like, I took a toy problem, I studied the Nash equilibria, here are a bunch of graphs of all the vector spaces, and here's how I think all these things converge, and like very focused on the actual training, because where we are in GANs right now is there. Where the real fundamental research is on toy problems, simple games, even things from, and because people are really trying to establish it, they're trying to pull in from a lot of other research. So that's why you'll see a lot more of the recent papers bringing in math and game theory and this, that, and the other to try to figure out how do we make this thing stable, how do we make sense of it, how do we put it into a schema, I guess would be a better way to say it. But their papers go kind of different ways. So, which is really kind of interesting that the original paper on GANs was much more a piece of engineering. That the mathematical foundation was kind of absent. It was more like I mean, there was some theory behind it, but it was really like, wow, look at what I could figure out how to do. And then people have kind of filled in a lot of the theory and the proof since then and try to figure out how to describe the whole thing. So yeah, 2-player games we're going to be talking about, and a lot of what we talk about here will apply to GANs, but it'll also just apply to game theory in general. Some of the stuff will be specifically GANs, and if you're not sure about which is which, just ask. But that actually is a great question. we also see that it requires a balance between the two players. So you are looking for an equilibrium where two players are kind of balanced, tug of war at a stable point, whatever. But you can end into a situation where one player is just beating the other player completely, or that they're having a cycle. So you can imagine that the generator is beating the discriminator. That means the discriminator doesn't know what's good or bad, even if the generator's implementing some. The generator could be producing junk, but if your discriminator is not strong enough to tell the difference between the junk and the real stuff, then it's going to keep producing junk. Or you can have your discriminator be way ahead. If your discriminator has a really sharp line and it tells the generator that everything it does is terrible and it's never going to be right and it's just doing everything wrong, then it's never going to learn anything. It's like, so these very careful balances that you have to establish between training these two parts now that we're dealing with two players. There is a stationary point when we're specifically talking about GANs and specific formulations of GANs, but there is no guarantee that you're ever going to get there. You can end up into all types of different cycles. One thing you'll see is herding. I kind of love bringing that up, just the Scott's lecture, but you see it in so many aspects of machine learning, and it's nice to just kind of put it all into one trope, which is this herding idea. It seems like a nice enough word for it. In GANs specifically, it's called mode collapse, so you will see that word everywhere in the literature, in the blogs, et cetera. But mode collapse is basically your generator starts doing just one thing. So you train it on all of the MNIST digits, and it will just produce 8s. Or it'll just produce like 8s and 3s because they're kind of similar. So you'll see it just do a very narrow part of the distribution, not actually cover what it's supposed to be covering. That's very similar to herding like we've seen in other situations. In general, adversarial problem is it's much harder than single-player optimization. It's the more general case. And you can think of everything in terms of n-player optimization and what you've done before as n being 1. Also, the discriminator, it's highly nonlinear. The gradient is very noisy. It might be non-informative. So while it does make sense that the discriminator tells the generator what to do, there are many situations where the discriminator is telling it nothing that useful.
Why does the gradient tend to be noisy?
Because you're putting it through a nonlinear network of 5, 10. Like you want to increase the number of layers as much as you can because it's deep learning. But as a result, the actual error surface ends up being like that. So you're here. I would almost want to draw that on the board if we have a. Because we'll be coming back to this as we're here. So like let's say your current generated data is here, and your current, well, not current because it's it's set. That's the actual x, the true x. And this is your generated functions of z. If your ideal generator is trying to tell this to move over here, right? It's trying to give it a gradient that goes over here. And your discriminator is a scalar. So your ideal discriminator would be something like this, OK? Because that means if you move these things along that gradient, you'll kind of nice and smoothly end up over here. But in practice, sometimes you'll end up with a discriminator that looks like this. And that means you have no idea where to go here. Or sometimes you'll have a discriminator that looks like that. And all of these things are kind of natural because you're dealing with neural networks and everything's, has, if you imagine this being a polynomial, you've got so many different dimensions, you've got so many things interacting, you're going to have some noise here. And a lot of what we're going to go into in terms of how to clean up GANs is trying to encourage them to be more like this guy and less like these other guys. So the real challenge in GANs is how do we do this? And on a more kind of fundamental level, taking it even with general neural networks, we don't have a great answer, which is like, how do you put an upper limit on the complexity of your neural network? There's dropout, there's regularization, you can not have too many parameters, like you can clip some things. There are a lot of answers. There's no real perfect answer, but that's kind of what we're trying to get at in GANs is we want to learn a function that's kind of nice and smooth in some way, and that way we can use its gradient. And if we get something that's noisy or something that's fully saturated or something else like that, that's another pathology, then that means that this guy doesn't actually know where to go. Another important thing to understand about GANs is that we're doing simultaneous updates. Frequently, this is called simultaneous gradient ascent. It's always called gradient ascent when you're talking with GANs. I don't know why. It's a little bit weird. But the key is that it's both players need to play at the same time. It's a dynamic system. They need to react to each other. And it's not just one or the other. The reason is kind of outlined below, which is the discriminator tells the generator which way to go. So if the discriminator hasn't been trained yet, then what's the generator supposed to do, right? That doesn't make any sense. But on the flip side, if you train your generator out all the way, if you train your discriminator out all the way, then this is what you end up with. Because if you imagine you train something with the sigmoid output and you train it for 100,000 iterations, it's eventually going to get these very flat, useless kind of curves. So you want to train the generator enough that it's doing this, but you also, like, if your generator was doing that, it would make everything worse, right? I'm sorry, if this is your discriminator. Right, yeah, so you need your discriminator to be better than the generator a little bit, but not too much better. If it's beating the generator by a lot, then it's going to output this guy, and the generator's not going to be able to use it. But if it's not trained enough, then it might be doing this, and that means you're pushing things in the wrong direction entirely. So it's trying to find a good balance between the two of them is another challenge to how we train GANs. One of the recent approaches to this has basically been you put a limit, you put something that caps the complexity of the discriminator. You have some sort of regularization that keeps it from getting too large, and then you just train it for more than enough for it to get trained enough. So you prevent it from being untrained by just saying, I'm going to train it like 10 times each time I train the generator. And you prevent it from being overtrained by putting in these other techniques, which we're going to go through a lot of options, but these techniques which try to prevent it from getting too saturated.
Are there techniques where you could take like a very well-trained discriminator and just have it give more information to the generator? Say like, yeah, you're on the right track, but you're still wrong.
On the right track, but you're still wrong. It's kind of that the discriminator needs to update each time. So like, if you imagine that this data then moves over here, then the discriminator needs to start going the other direction. So there's no like, there can be a very well-trained discriminator, but only for a given set of generated data. Because as soon as the generator changes, it's no longer a good discriminator. It's only a good discriminator for a given generator.
Okay, I guess I'm getting at the idea of like, you have, taking from game theory, you have like a very well, you know, an expert player as your discriminator, and it can tell the generator, the more novice player, like, you're still going to lose in this position, but you did make a good move given your bad position. You know what I mean? So you have more information than just like thumbs up.
Well, I mean, it's not a thumbs up, it's a thumbs down. It's a neural network with gradient, you know. You're actually backpropping through the entire discriminator network. So it's giving you information on every single thing, but that's the noise we're talking about. Like this is basically what happens to a lot of the information we were talking about is it's telling you the gradients that you need to do to increase its score for each of the items there, and you're just backpropping against it. So it is a first order approximation, but that's kind of the best we do in most neural networks.
Yeah, you're literally talking about the slow pizza case that is called about.
Right, yeah. So the discriminator output is only one scalar, but that scalar is connected to each element of the input, and it's actually giving gradients with respect to, you know, every single thing. So when you think about what it's telling you, it's basically giving first order approximation of how to change your image to a better image. But whether that first order approximation is good depends on this thing. You know, because if you're over here, then the first order approximation is telling you to go slightly here, and you just bounce back and forth. And that's where we get to all the optimization issues. Is there another question? OK. Keep an eye on time, I guess. So this is the balance between D and G. We talked about that a little bit. But the idea is that if the discriminator is not good enough, then training the generator actually makes the generator worse. And if the discriminator is too trained, then it's not really telling the generator anything because it's been squashed or it's noisy and there are other issues. So you want to have a nice balance between them. In terms of how you actually do a balance, there are many more advanced techniques to get to, but at a fundamental level, the things that are affecting the balance, there's the complexity of the networks. So if one network has a lot more layers and a lot more parameters, it might end up learning a lot faster than the other network, and it might end up getting ahead. You also have learning rates, because each one of these has different learning rates. It might have different optimizers. Those can affect which one's kind of winning or losing in this equilibrium. You can also train them multiple iterations. So as opposed to just changing the learning rates, you can train the standard one is discriminator 5 times and then generator once, then discriminator 5 times and generator once. So you might have the same learning rate, but it's getting 5 batches every time the other guy gets 1 batch, so you know the discriminator is a little bit ahead. But maybe if you turned that to 10 batches on the discriminator, you would start to end up with this kind of saturated solution. So setting that number of iterations is a hyperparameter that people have to kind of play with. There are a few papers which recommend different types of dynamic schedules. Those involve things like checking to see the losses and then training the discriminator more or the generator more, depending on which guy seems to be ahead based on several different heuristics. So there's a lot of more engineering and less math that goes to that. But you can imagine many different rules of thumb in terms of when you want to start training one versus the other and kind of adjusting the ratio as they learn. But there are many different factors is kind of the point of the slide, because every time you change one thing, something else might be off. That means you give your discriminator 3 extra layers and a bunch more width. Maybe now you have to train the generator with a slightly higher learning rate. So pretty much every hyperparameter in GANs is interrelated in some complicated way. And as one of them starts to get off from another one, you will end up into these chaotic kind of cycles, and things will not start to work. And that's really what the brunt of current research has been, is ways to make them more stable and more resilient. So initial GANs were very much like, here's the set of parameters that works. Change any one value, and you will get junk. And with kind of more recent updates, it's been much more kind of widening the range in which things work. So they're more and more resilient. They're not perfect now, but it's been kind of an incredible improvement in just a couple of years. There is a stationary point. This is the ideal equilibrium that we want to hit. At that stationary point, the generated data exactly matches the real data. In the case of our traditional GAN, oh, sorry, that slide's still messed up. Just say the discriminator should output 0.5 for all points. So basically, that's what it's saying, is if X and G are on the same point, then your discriminator has nothing to do, so it's just going to do a straight line straight across. That's the minima that it gets. And if the discriminator is drawing a straight line straight across, then there's no gradient for the generators to do, so the generator stays where it is. That's basically your proof in layman's terms that there is a stationary point. That does not mean you will hit it, but that is what the stationary point looks like if you ever were to get there. But in practice, we have a lot of issues getting to it, and we're going to talk about the ways to kind of regularize ourselves towards that point. So in practice, we're starting with something kind of unrelated to GANs, or not unrelated to GANs, but something with just simple games and gradient descent. So as a little bit of explanation, I'm hoping we can click. If not, I'll just have to scroll for it. It's a little hard to see on the screen there. Oh, shoot. I should bring it over on my screen. All right, so this is a kind of simple animation I did of what gradient descent on rock, paper, scissors looks like. So everyone knows the game, I'm assuming. Rock beats scissors, scissors beats paper, paper beats rock. So if I'm playing rock, you guys should all play paper. OK. Now, here's where it gets interesting. Let's say I tell you that I am randomly picking one of the 3 each time. And I'm picking rock 40% of the time and the other 2 30% of the time. What is your best strategy? Your best strategy should be paper 100% of the time. And that shows you why this is what's called like an unstable attractor. There are a lot of words for this. You can start going into Nash equilibrium, et cetera, et cetera. But the problem is if one guy is slightly off from the equilibrium, the optimal strategy for the other guy is to be 100% on the argmax of whatever the other guy has and to exploit it completely. And because of that, you can play really, so this is a very simple game. It's just, each player has 3 parameters and they play with it. But if you play rock, paper, scissors and you start off at basically any starting point, it will actually start making oscillations, and the oscillations will actually start growing and growing and growing. And you end up with, this is not a GAN at all. This is just a 2-player game. And this is meant to illustrate the point that when you play a 2-player game with gradient descent, each player is doing the thing that at that point in time makes themselves better. And yet you can end up with these complete loops. And the last part of that video is one of the strategies we're going to talk about next. So yes, question? Oh, yeah. So in terms of the way you fix that, that was the way. And very quickly, it sounds very simple because I'm just ending up on telling you, oh, the best strategy is to just equally throw each of them, and that's the best strategy for both people. But actually hitting that strategy when the 2 people are playing never happens with gradient descent. We have a couple of the videos, but I think we're running a little long, so I'm not going to go through all of them. Oh, I'm sorry, the video's still going, isn't it? OK. So we have some of the videos. I can come back and put these, but they show you kind of the chaos of actually running a GAN and what it looks like. So there is theory, but when you actually look at where the discriminator is and where the distribution moves, you'll get a sense of it's incredibly noisy. It doesn't really hit where it's supposed to go. It moves in leaps and jumps. So we'll see through the actual GAN training what happens. But these are all kind of videos of traditional GANs. So we're going to talk about the kind of the standard failures of GANs so we can understand what people are doing to kind of fix them. The first one we talked about is called mode collapse. And this is a video I actually do want to pull up for you guys. So mode collapse, as we said, is when your neural network only learns 1 or 2 things out of the distribution. So this is someone actually training MNIST digits. And you can see what happens. This is kind of what a GAN looks like as you're starting to train it, and the digits are starting to form. And you see it's got some 8s, it's got some 5s and stuff. But then slowly, as it trains, the outputs actually start to converge to a single point. And by the time he's done training, this is basically the outputs of his network. Keep in mind, this is trained on 10 different digits. But for whatever reason, this particular time, 1 was where it happened to find its stable point. And its entire distribution is just not covering anything else at all. This is your standard mode collapse.
Is the intuition around that the generator started generating things that were fooling the discriminator, in this case of 1, because maybe that's simpler?
Yeah, it's
Good marks, and they just said, OK, let's go for it. Let's keep doing 1s.
Yeah, there are a lot of kind of intuitions for why that might happen. I'm going to erase over here. One of the problems is it's a very noisy gradient, and it's hard to tell the generator to break up. And as we see in other neural networks, it's very hard to tell something to be different. It's very easy to tell things to be the same or to do something specific, but it's hard to tell them just go in separate directions. So if you have some generated points here, and these are your generated points, and your real points are here, and let's say I've got some other real points over here, what you're going to have is you're going to have a generator that kind of does, your discriminator is going to kind of do that. And then if your generated points move over here, your discriminator is going to kind of do that. And it's going to be kind of roughly like this, and then it's going to have another bump over here. So it's your standard problem with how do you do gradient descent or gradient descent when you've got something that's non-convex. Because it's you're over here, and you want to go to a maxima, but you're not going to see that the maxima isn't just this one, it's this one over here. That's just your fundamental issue with a lot of gradient descent, but you see it much more predominantly in GANs, because that's over here you've got your 1s, and over here you've got your 8s or something, and it just eventually kind of all pans out to that end. And there are a lot of theories as to exactly why that happens, and it's some combination of all of them. And there are a lot of theories on ways to make it stop happening, and the right answer is probably some combination of all of those. But I wanted you to see what an actual mode collapse looks like. Sometimes you'll see cycles. So instead of everything just being ones and settling in at ones, they'll all become ones, then they'll all become eights, then they'll all become threes, then they'll all become fives. So you'll see them actually cycle through a bunch of different digits, but never actually spread out to any one particular digit. I don't have a great video of that, but it's actually very fascinating to kind of see visually what it's doing.
Is that the same reason as the rock, paper, scissors thing you saw?
Partly, yeah. It's a two-player game, and it's not going to hit an equilibria except certain specific conditions. And here is an interesting kind of just, it's a failed GAN that doesn't fit into any clear category of what the failure is, but this is by no means a weird thing to happen with GANs as you're training them and trying to get them to learn something. This is CFAR10 images, as you can tell. This is a GAN trying to learn CFAR10 images. And this is the kind of chaos you will sometimes see, is it's just going through all kinds of weird loops of things, but it's never actually settling down on any particular thing that, I mean, it looks like a Technicolor slightly version of CFAR10 images. But this is the type of thing that happens when GANs do not work. So you guys see plenty of papers where GANs do work. I just want you to see some pictures of here's when they don't work and all the things we can do to try to make them the good stuff and not the bad stuff. So what that brings us to, and we've been kind of like preluding to, is there are a lot of techniques that people have come up with. This has been a ton of research, a ton of literature. People have been going crazy over different ways to do it. Everybody claims that they have the golden bullet, that they've like fixed GANs, they finally got it correct. There are all these papers that make these claims like, in all of our experiments, we never saw any evidence of any mode collapse. And the next paper will be like, we tried their stuff and it kept having mode collapse, and then here's what we did. And like, so there's been a lot of back and forth, a lot of noise out there, but there's been enough, as much as people don't really understand the math and the optimization, there have been enough people that actually get results that look good that it's kept things kind of going along. So those are the two different tracks, really. But there are many tricks. Some combination of tricks might be the right thing. A lot of people are suggesting different combinations. And we'll take you through kind of what they are. The important thing is not to memorize any particular one implementation, because that might change next week. The important thing is kind of what are they trying to do? How does it work? How do they do it? And there's the intuition of the types of things that people are working on. If you guys are interested in this type of stuff, it's clearly a current topic. So the optimization techniques we're going to talk about, it's kind of a hopefully not too long list. We'll skip around depending on how much time we have. But these are a very, very small subset of the GAN papers from the last couple of years. I guess we only have one up to 2018, mostly 2017s, 16s. But anyways, we'll be going through each of these. We don't need to look at them right here, but that's just your kind of heads up and bibliography if you need it. And as we said, very active. Some combination of these might be the right answer, maybe something else entirely. So to start with, unrolled generative adversarial networks. This is what we saw at the end of the first video I showed you guys. The problem is that GANs have trouble reaching this stationary state. It's because they're making decisions that give them the best benefit in the current moment. They're being very greedy. Pardon me. I'm going to try to beat you as best as I can right now. You're going to try to beat me as best as you can right now. And we're never going to hit a good, stable point. Versus what unrolled generative adversarial networks do is they actually try to make decisions based on what the opponent's reaction is going to be, which is kind of a fascinating idea and also very easy to intuitively understand what you're trying to do, which is you're not just trying to update your generator such that it gives you the best results on the current discriminator. You're trying to update the generator so it gives you the best results on what the discriminator is going to be after the discriminator does gradient descent. So that's what these equations are trying to break down for you, which is the second equation there. Well, the first equation is just your base term. Don't worry about that. But your second equation is the actual recurrence relation, which is gradient descent, right? It's that your discriminator at your next step is your discriminator at your previous step plus some step size times the gradient with respect to your discriminator weights. So pretty straightforward. That's how gradient descent works. So what's fascinating here is you can actually backprop with gradient descent in the mix. So you're not trying to optimize against your current discriminator. You're trying to optimize against discriminator k, which might be 5, 10, 20 steps into the future. So in terms of what it's actually doing, if you have a kind of dependency diagram here, you see the dependencies actually go through SGD. So you take your discriminator and your generated weights, you perform SGD, you get some new data, and then you do it again, you perform some new SGD, you get new data, and at the end, you've got what your discriminator is giving you after 10 steps of gradient descent, and you can actually perform gradient descent on that. So this was kind of a very broad in scope idea. It came out relatively early in this whole GAN story. Practically speaking, it's harder to implement and a lot more on your forward pass, because basically for each one step of the generator, you're doing a forward and backward pass through many different steps. And the more complicated your optimizer is, the more complicated this actual gradient descent is going to become, because you're actually doing gradient descent through your optimizer. So unfortunately, unrolled GANs didn't really catch on, but what they do is kind of the foundation for a lot of the later papers we'll see, which is just the general idea that your generator isn't just trying to do what's best for itself right now, it's trying to do what's best for itself right now, including what the discriminator might do next turn and the turn after that. So it's trying to do the best for itself while the discriminator can't kind of retaliate. So it should be relatively intuitive, which is also why I like to start with like that. So, so here, you can kind of think of it like chess. You're not just making your best one move, you're making your best move considering what you think the opponent's going to do. So it has this intuitive logic, it works out mathematically, engineering-wise, a little harder than some of the other things we'll look at, but a great place to start. Any questions about, oh. So here's just kind of a toy problem. This is the type of illustration you will see 100 different times in GAN problems. People love to do these kind of circular little toy problems to see what happens. So the first row is evolution over time with the unrolled GAN. So you can see it starts from initialized at a center point, and it kind of spreads out eventually, and then narrows to points, and it gets the points. And at the right is the target. Versus the bottom row, you see a traditional GAN, and you see it actually just kind of rotates around through different points, and eventually it stops at one of the points. But this is your stereotypical mode collapse of you trained it on a circle of dots, and when you trained it, you got one dot. And that one dot happens to line up with one of your dots, but what about all the other dots you gave it? That's your mode collapse. And they also have some nice illustrations of running it on the MNIST data set. So on the bottom, you see some typical results of a GAN that doesn't have great hyperparameter settings. This is kind of what you expect to see as you're trying to find the right settings for your GAN. As I said, it's very different than VAEs. If you have a VAE and your hyperparameters are all wrong, then your output will be blurry. That's pretty much the worst that can happen. Things might be a little blurry, things might be a little off, but you're not going to get just chaos, or you're not going to get noise, you're not going to get cycles. Versus in GANs, when things are off, this is kind of typical of what you can expect. So that's it on the unrolled GANs. I guess any questions on that particular technique before we move on to the next guy? Any questions on the stream? OK, we sound good. So then what we're going to look at is kind of improved techniques for training GANs. This takes a different approach, which is more, we're going to throw a tool shed of different small techniques which might individually help out in a little bit. So they propose actually, this was a very, very big paper, a very long list of authors with very important authors on it. So that's kind of why a lot of people reference it. But they actually threw 5 different methods together and are claiming that some combination of throwing these different 5 together are really what's going to make GANs converge. So one technique they use is feature matching. This is the idea that instead of just being kind of one scalar that your discriminator is outputting, what your discriminator is going to do is it's going to learn a space. It's going to learn a set of statistics. So the way this works is generated images much match the statistics of real images. So it's not a point-by-point comparison it's actually taking expected values of given statistics over generated and expected values of given statistics over discriminated, or over the real values, and then trying to minimize the L2 between them. So the equation is here at the bottom. It's the expected value of x drawn from your data of the f of x. Your f is this discriminator, which is giving you a space. The distance between that and the expected value of z drawn from z, that's your latent space. That's being put into G, which is your generated images, and then that's being put into F2. So it's the distance between what F gives you for real stuff and what F gives you for generated stuff. So this one's changed. I'm sorry?
F is the function.
Yeah, F is the function. F is taking the place of the discriminator in your other. Instead of your discriminator transporting things into a single scalar, your discriminator is putting things into a full space, and then the scalar is that guy. So it's like the last part of your discriminator. Instead of being a linear network and a sigmoid or something, that last part is an L2 difference between two guys. The other important difference is that it's working on expected values, not point-by-point instances. So they theorize that it might be a little better at doing things that matter on a population. So what that's kind of more explicitly in our next technique here, which is mini-batch discrimination. So this is one of the stronger techniques to avoid mode collapse. The idea is that the discriminator looks at multiple samples before deciding if all of those samples are wrong or all of those samples are correct. And this makes a lot of sense for several reasons, but it basically gives the discriminator the ability to make better decisions based on statistics. So let's say if a generator is collapsed, that means that it is producing a given point that is a real point more than it should. So it's producing 100% ones instead of 10% ones. But the ones it produces are still ones. That means it's hard for the discriminator to tell the difference between a 1 from the real data set and a run from the fake data set, because they both look like ones. The difference is that the population is much higher. But if you're looking at a set of samples, if you take 10 samples from the generated data set and they're all ones, and you take 10 samples from the other guy and they're not all ones, it's really obvious which one's the generated data and which one's the real data. So looking at more samples should intuitively make it easier to tell the difference between the real and the generated, especially when you're dealing with something like mode collapse. And because it gives you that extra power, it kind of discourages mode collapse, and that's basically what they found. That by including multiple things in their discriminator, and their discriminator not just looking at one at a time, it encourages your diversity. And that's one way to address mode collapse, and we'll see many others. Another technique they introduce is what they call historical averaging. This is meant to address specifically the cycles that we saw. So you can end up in cycles. This actually doesn't take too long to explain. You can end up in cycles. You add a regularization term that says, try not to cycle too much. It's basically just saying your current parameters should be like your parameters used to be. Try not to change them too much. And that ends up basically reducing your cycles. Pretty straightforward, but a simple technique that they use in combination with others to try to stabilize the whole process. Another technique proposed is one-sided label smoothing. Hopefully all of you guys are aware of smoothing, might have wanted to use that in some of your homeworks. It's a great technique. It tends to help everybody out. So smoothing is good in general, so why not try smoothing with GANs? However, what they found is that it works better if you use one-sided label smoothing instead of smoothing both labels. So if you smooth the real labels, then that means that you've got a nice smoother distribution for your real labels. It's not a really sharp point. That part makes sense. The problem with smoothing your fake data is if your discriminator is trying to output a 0.1 for fake data, then you're not telling the fake data that it needs to move out of that area. So you want that to be 0, so you're sure that your generated data is getting out of there. Because if you're setting that to be a 0.1, then you end up with a situation put it right here. Yeah, so if this is your G and this is your real X, if you're smoothing a little bit, then you end up with a situation where that's what you're telling it to learn. And if you're telling it to learn that, then obviously your generator is not going to move out of there. Because if you're saying, this is like 0.1 and this is 0.9. So that's why they're saying one-sided label smoothing is the way to go with traditional GANs to just make them a little bit more stable. But as we're going through this presentation, we'll see people are stopping using cross-entropy loss altogether, so maybe this doesn't apply as much anymore as we progress through time. Virtual batch normalization. This one was a bit of a one-off. No one since this paper has even given it like a nod, roughly, as far as I can tell. But it's an interesting idea that they did, and the idea is that they took a reference data set in addition to, or not data set, but they took reference samples in addition to the samples that they were actually training the batch on. They generated their statistics based on the reference data set and then used the reference data set to do the actual normalization on the other data set. So what that ended up doing is they have to do 2 forward passes for every batch and kind of arguable whether it actually improved or not, so that someone explains why it didn't catch on, but I mentioned it as something that happened to be in that same set of techniques. But that was kind of their last technique they mentioned, so I guess the weakest hitter on the team. For a bit of a different approach, this one's just a one slide, what someone tried to do. It's called least squares GAN, and this was in 2016 where everyone was just kind of throwing out ideas, and I think things have kind of settled down since then. This is the idea of instead of having the labels trained by cross-entropy, if you guys remember from last time, we talked about how original GANs are cross-entropy loss. You're trying to get a 0 for, your discriminator is trying to give you a 0 if you're fake. It's trying to give you a 1 if you're real. In this situation, they changed it to using just a L2 distance. So they're trying to give it a 0 if you're fake and a 1 if you're real, but the loss is the square distance between what you're outputting and what it's supposed to be. It's not a logistic function or anything. It's still nonlinear, but it's not quite as nonlinear as cross-entropy is. I don't know if you can really quantify nonlinearity, but something in that genre would be the way to describe it. So they are trying to clean up the loss function a little bit, make it a little smoother, make it a little less likely to saturate. That's the general idea of what they're trying to accomplish here. To just kind of have linear units and minimizing the squares as opposed to something more complicated. This one also did not kind of get picked up, but it's good to see as kind of a stepping stone where people were trying to make the loss functions, which we talked about before, which are based on cross-entropy loss, into something that's a little bit smoother, a little bit cleaner, a little bit less likely to oversaturate. Here we have another kind of approach in another direction of how to try and smooth things out. So I thought this was a nice, simple and intuitive idea, which is basically they're just putting noise into the images. Sounds simple, but it works. The idea there is if you have some noise around your X and you have some noise around your generated data, then you're causing some smoothing to say that it should be a little bit flat in that region. If you just have one X that's right here and you're saying make this X a 0, it might learn something that looks like this, right? It might learn something that just goes up and down and right about. But as soon as you start to smooth out a little bit, you're starting to say things are a little flatter. So that's a theme you want to keep in mind as you go through all these techniques, that a lot of them are different ways of trying to make things flatter in a very simple way.
So how does making it flatter allow you to avoid that? Say it's a local.
Well, it's this situation of if you're saying something that's a little bit flatter, I'm saying something looks a little bit more like this, and it looks a little bit less like that.
So think again of the logistic. Suppose you had very clean data on both sides, then it's easy to fit a logistic into the perfect steps. But if you add noise, you're going to have the clean leak over into the, the positive leak over into the negative and vice versa. Then you're forced to fit in a smoother logistic.
Yeah. You want something that looks more like that and less like this in a very layperson sense, but in terms of how to do it, so many things, but noise gives you that idea of you just,
Noise is very
you want things over here and over here to also be that one value, as opposed to just one guy right here. So that was actually the entire slide on that paper, but it's a simple idea, and we'll work off of that. Now we see, as we work our way into energy-based GANs, people are trying to unpack and make the loss function even simpler. So this is the simplest loss function at this point in time. It got even easier. But what you see is they kind of unwrapped all of the cross-entropy mumbo-jumbo that's going around it. So instead of trying to minimize the negative log likelihood of what the discriminator is outputting and 1 minus the negative log likelihood of what it's outputting in another situation, it's just outputting the discriminator value minus the discriminator value for the other one. Very straightforward. So these are actually written, I think, in terms of the energy-based GAN wants the discriminator to output very low energy for the real values and very high energy for the fake values. So that's why it's a little bit different terminology than some of the other GANs. But basically, that's all it's trying to do. It no longer has a probabilistic interpretation. In your original GAN paper, you're training it with cross-entropy. Your discriminator has an output value. That output value is the probability of something being real versus something being fake. It actually has an interpretable probabilistic meaning to it. Versus here, it's an energy number. It's a score. We're not really worrying about assigning a meaning to it, but we're saying that you should give a high value, or I'm sorry, we're saying you should give a low value to real data and you should give a high value to fake data. And then the generator is saying, try to get the lowest possible value for your fake data. Very straightforward, same intuition as your original GAN, but we've taken away the logics, basically. We've taken away the logs, we've taken away a lot of this extra stuff that's making it nonlinear, that might be causing it to saturate in certain situations, and we're trying to get something a little bit cleaner. The difference we'll see between here and what we're going to go to in a slide or two is that the energy-based GAN chooses to use this plus right here as a ReLU. So they're basically doing like a max margin type entropy, or sorry, max margin energy difference that they're trying to establish, versus in later papers we see they just try to maximize the difference. There's no margin or anything involved. So that brings us to Wasserstein GAN, which is what we've kind of worked up to, somewhat of a natural expression of the energy-based GANs. The problem with the energy-based GANs is that their outputs are unbounded. Because we're basically saying, you give us linear outputs, and your loss is the difference between these linear outputs and those linear outputs. So it could be anything. It could be completely unbounded depending on how much you train it. Wasserstein GAN is where we started realizing we need to put some constraints on the complexity of what the discriminator is learning, and that means we can train out our discriminator and not worry about overtraining it. Because as long as we have some upper bound on how complicated it's going to get, then it's just train it for long enough, and you're fine. So what they do is they use a linear loss instead of logarithmic loss. That does make things much cleaner, but on the flip side, things are unbounded. So they deal with the unbounded issue by putting weight clipping onto the discriminator weights. Very straightforward to implement, ends up actually not working very well, as we'll see with later papers, but it's a simple idea. It's just every single element of every single weight vector gets clipped to some maximum value. Absolute value is only a certain number. That means that your Lipschitz constant for whatever function it learns has some upper bound. And as long as there's some upper bound on the Lipschitz constant, then a lot of our theory ends up working out in showing that GANs actually work pretty well. So what this means is it gives you a smoother gradient than the traditional GAN. We see the equation down here. That's the supremum over functions that have a Lipschitz constant less than equal to 1. And this part here is really similar to what we saw with the energy-based GAN. It's just trying to give the expected value for this guy minus the expected value for the other guy. There are no logs or anything in here. There are no exponents in here. It's just the difference between the actual raw values output by the network. So why the name? This is an important aside. I don't know if you guys actually know what Wasserstein or Earth Mover relates to. This is kind of what we were talking about earlier about people are starting to make more of a like, hey, math and machine learning can get along kind of discussion. But anyway, so Earth Mover is the total mass times distance that you have to move to make one distribution into another distribution. So it's very different than, like KL divergence is the thing we use like 99% of the time in machine learning. But Earth Mover is a little smoother, and it tends to work out much better for this problem. But I want to just explain what this formulation is and what it does, and why it's called Earth Mover. So it's called Earth Mover because it's like literally, if your probability distribution were piles of dirt, what is the least amount of dirt you would have to move the least distance? So like, if this is P and this is Q, then the Earth Mover is like this height times this width. And if Q was over here, then the Earth Mover would be this height times this width, right? That's your Earth Mover distance, because representing, oh, I need to pick this thing up and carry it over here, or I need to pick it up and I need to carry it all the way over here. The reason this is different than something like KL, as we'll see on another slide, is if this is like your Dirac delta and this is a Dirac delta, then the KL between these guys is infinite. And that is not very good for something we're trying to do gradient descent on, because basically KL in certain situations is like always infinite and then 0 and then infinite. That's not what a nice looking thing that we want to do gradient descent on is. We want something that goes nicely up and nicely down. So in terms of what Wasserstein is, it's the infimum over the gammas that are drawn from pi, yada, yada. They like to use Greek symbols. But basically, you have some set of mappings between your real distribution and your fake distribution, and you're trying to find the minimal mapping between them. What mapping between them minimizes the amount of stuff you have to move for the amount of distance? So on one hand, EM has a lot of great properties, but EM is very hard to complicate, to actually calculate. EM relates to what we call the optimal transport problem. It's NP hard. Like, there are a lot of solutions for doing a lot of things that make it a lot better, but practically speaking, solving for which set of input points is the closest to which set of output points without duplicating anything is a combinatoric and complicated thing to do. So the connection that this is making is that we are using our GAN to basically solve a dual of the Wasserstein problem. So here we get to kind of why Wasserstein's nice, which is if you imagine this P and this Q, and you imagine this distance here is what they're calling, theta, whatever. So this distance theta, using the Wasserstein distance, the distance is theta, right? Because if you move it 10 away, then the distance is 10. If you move it 20 away, the distance is 20, whatever. Using Jensen-Shannon, you end up with something that is piecewise. All of the traditional types of functions that we use end up working out as those being the divergences based on theta. So that means basically you've got something where it's 0 if your function lines up with the function it's supposed to be, and it goes to infinity everywhere where it's not correctly exactly lined up. That's not something that's going to be amenable to gradient descent. Visually speaking, this is kind of what we're talking about. If you're trying to minimize the Earth Mover distance between 2 points, you get this nice little function there on the left, which is, follow the line, and you'll eventually get to where the point is. And then you can barely see it on the right, which is Jensen-Shannon, but you see the dot in the center at the bottom, and then everything else a line at the top. And that's basically, that's your discontinuous function, which is not going to be helpful for actually trying to find where you need to go. And I think this relates back to what we were talking about before about if it overtrains, that's because there's such a difference between the two of them. It's infinite. So here we see kind of visually what you end up getting when you train the W GAN as opposed to your regular GAN. So on the left, we have your generated data. On the right, you have your real data. These are just 2 Gaussians next to each other, nothing complicated there. But what they're trying to show is that you train the W GAN, You can train it for 100 iterations. It's still going to learn a nice, relatively smooth line going across. That's what it learns. Versus the GAN discriminator, the regular discriminator, you train it for 100 iterations. It learns, a step function, basically. So the GAN in this situation, you cannot use the gradient. It's not useful. But the WGAN, the gradient, continues to be useful. You really can't overtrain it, is what they're trying to say. Question on this guy? OK, so the connection here between, we were talking a little bit about Lipschitz constants, a little bit about Wasserstein. What does it all mean? What it comes down to is that the dual of the Wasserstein metric is solved by optimizing over functions with a Lipschitz constant of 1 or less than 1. So that's the infimum we saw on another slide. In terms of the actual derivation, it's relatively long. But the way you can kind of imagine it is the connection between the Earth mover distance and distance here. OK, so let's say this is my discriminator, and it has a Lipschitz constant of 1. So basically, let's just say this is the function y equals x. It's a straight line. Slope is 1. OK? If I'm saying the distance between two things on the x-axis is 5, then I could also just take the distance on the y-axis. The distance on the y-axis is the distance on the x-axis. That's why your Lipschitz constant of 1 is required for your distance. So basically, that means if I have a point here and I have a point here, f of this point minus f of this point is how far I need to move. That's all it's trying to say. So this was kind of like the earliest connection with like, hey, maybe GANs are related to Lagrangian, yada, yada. And then as the literature has kind of evolved since then, it's become much more of a stronger comparison between the two of them. So Wasserstein GAN, more stable than traditional GAN. Loss values are more meaningful. But the problem is actually when you do it, it doesn't work out that well. It just doesn't train because things tend to get saturated. So that brought up the response paper, which is improved training of Wasserstein GANs. It's called IWGAN or WGAN GP or whatever you want to call it. But it's similar to WGAN, but it's addressing this Lipschitz idea in a much more direct manner. So if our goal is to say, I want to learn a neural network who has a Lipschitz constant of 1, you could do it with gradient clipping or whatever, or you could just like calculate the gradient and make sure it's equal to 1. And that's basically what they're doing here, is that they have this gradient penalty term, which takes samples from somewhere in your input space, and we'll talk about how it gets that. But it takes the samples, it calculates the gradient at those samples, and says the gradient should be about equal to 1. What does that mean? That means you're not going to have really high gradients in your function anywhere. You're not going to have really sharp things anywhere in your function because your function is going to have a gradient of about 1 just about everywhere. Pretty straightforward, and that's how they are approaching the idea in general of smoothing. So they're both in one sense, they're smoothing it, and you can understand why it works because it smooths. In another sense, you can understand why it works because it relates to the Lipschitz constant and it relates back to our Wasserstein GAN discussion. So in terms of what they write here for the actual loss, you see something similar to energy-based and Wasserstein GAN. See, there's no scaling, there's no logs or anything. It's just the expected value of one minus the expected value of the other. One's drawn from generated, one's drawn from real. But then they have this extra term, which is just the difference between the gradient and 1. So the gradient should be about 1, and it's the squared difference from 1 that they're using as their term. If everything's 1, the regularization is 0. If it's not 1, then they have regularization loss. So it's not really guaranteeing that it's going to be 1, but it's regularizing it towards 1, and that seems to work in practice. How they actually do this, then, is that they have basically the same thing as a WGAN without the gradient clipping, but they additionally sample data that are linear interpolations between the generated and real samples. What that means is you can't really guarantee that your function is going to be a Lipschitz of 1 everywhere on the input space, because that's impossible to do analytically. And if you do it through sampling, you can never cover everything. What it's saying is, let's just look at the regions that are somewhere between our real and our fake data and make sure the path between real and fake is a nice, smooth line. And as long as that's guaranteed, then everything else is fine. So basically what you're doing is you're taking, here's your G and here's your D, and you're saying everything in between here, take those samples, and these should all be equal to 1s. And you're just going through them, you're randomly sampling them on each iteration, and you're applying that regularization term. In practice, here's what we see. So the top is the original WGAN. WGAN did they did absolute value clipping of each individual item, and that means this is the actual generator or discriminator that it tends to learn. It learns discriminators that are not good. They all have straight lines, basically. The implementation tends to side towards things that are straight lines and fully saturated, but don't actually fit the data well. Versus the bottom, you see the actual discriminator tends to fit very well. The top line, the discriminator basically fits as well as it can given completely straight lines, which is kind of nonsense, actually. But that's the results you get out of the WGAN paper. And then a kind of better comparison here of why that's happening is you see in the upper histogram, those are the weights that are learned when you do weight clipping, which makes sense, right? If you're clipping the weights, then they're either going to be at the maximum value one way or the maximum value the other way. They're going to tend to saturate either way, but you end up with pretty much all of the weights being 1s or -1s or whatever your scale is, and that's why you see these very straight lines, very saturated. Versus when you're applying their proposition, you end up with weights that look kind of like you would hope. That's a roughly Gaussian. You know, I haven't tested it, but that's kind of your ideal nicely looking weights, and that's what they get versus the junk from the original WGAN. So actually, that's the last slide on the IWGAN, but I think that's a pretty important paper to go with. I've got 5 minutes left, so I might just skip a little bit through a couple of the other ones. This is an interesting paper. You guys can definitely read everything on your own time. But what they're adding a term here is, as we talked about before, you're trying to stabilize your discriminator. So this is a term which is the gradient of the discriminator you're also trying to minimize. So back to our discussion about unrolled networks. How much improvement does the discriminator have when it trains? That is the gradient of the discriminator with respect to the weights. So if you can do something where the discriminator doesn't have a good gradient, then that means that the discriminator is not going to be able to come back and beat you with the next move. Roughly what it's trying to say. So as long as you're doing your updates that are doing the best for you while also reducing how much gradient the discriminator has to work on, that means the discriminator can't do something in the next turn that suddenly does something very well. Versus the discriminator has very high gradients, that might mean you're doing good now, but the discriminator is like one step away from beating you. So this theme we're going to kind of see together, that term of something that's relating to regularizing the gradients of the discriminator. So this is a kind of more complicated paper. It might take more than a few minutes to go through, so I'll try to breeze it. But the numerics of GANs is basically saying that the stable regions are the points where, where players are equal. That's points where you have 0 gradient for both players. So your ideal region is where, that doesn't mean that you're at a minima or a maxima or anything. That just means you're at a point where nothing's moving. So you can regularize towards those points. So there's the 2-player game, and then there's also this consensus part, which is going to a stable region. So both players are trying to do the best that they can, but they're also regularized towards, OK, can we just stop fighting? Can we go to some place that's if there's a place where we both have less gradients, then that's cool with me. De-escalation or whatever you want to call it. So basically, there's this vector field, which defines, if you're looking from the point of view of both players simultaneously, what kind of way is both of your parameters going to move simultaneously. So we have a vector field here, and we're going to regularize our vector field with another vector field, which is just trying to go towards the stable points. So we've got our original stuff where you're trying to win the game, and we've got an additional part, which is this L they call right here, which is the squared of V. V is what they call their gradients. So basically, you're trying to minimize the square of the gradients as well as trying to play the game as best as you see fit. The two of them are mixed together by this little gamma thing they throw in there. But basically, these are smoothing them out. And I've got an illustration here that should be helping you out. So what this shows on the left is here's a field that it has some equilibrium points, but it also has some saddle points. But you see, you're not necessarily guaranteed to go towards the equilibrium points. Then we create another field, which is just like arrows pointing towards all the equilibrium points. And then we have a mix between that field, which is just, calm down, go to an equilibrium point, and the try to win your game. And that gives us something that's a little bit in between the two of those. It's a little bit smooth. So it's not guaranteed to converge because it's not entirely the conservative field, but it's a little more conservative than the non-conservative field. So it's just a little bit of regularization on that end. But in terms of what it's doing, you see, again, a term which is the squared of the gradients, which you saw in other papers. I love the title of this one, by the way. But How to Train Your Dragon. This is another approach to how to learn smoothing. So we see that we have extreme gradients, sharp peaks, things like that around the real data. That's what we were talking about before. We don't want to have these really sharp items. So we just want to reduce the gradient in a region around the data. We want to smooth things out in a small area around it. And the way they do that is going to be very similar to what we did to what we saw in other papers. But experimentally, they found some interesting points about offsetting it with a k and about doing a max as opposed to just the value. But basically, they're adding a regularization term, and that term is as well the discriminator's gradient squared. So we're seeing a lot of these kind of similar ideas pop up with slightly different notations, slightly different ways of putting it together, and exactly which formulation is going to give you the best results depends on which author you ask. And I want to just show you these to kind of give you a sense of GANs. This is similar to the plastic GAN we talked about last time. Basically, they build up GANs that work on small images, and they work it up to big images. And the quality of the results they get in here are kind of astounding. I don't know why the links aren't working in Chrome here, but I'm going to fill them up later, actually. But actually, hang on. Actually, we got a minute, so I'll come back to that part. So we can talk about that one a little bit. Here's a paper on just primal dual methods and a little bit more about the connection to optimization and how we actually do this. It's just interesting to note kind of the comparisons. In terms of what they actually do, they add in some extra like kernelized based probability distribution here. So they use, so you do actually end up having much more there. So they are difficult to analyze, they're difficult to train, they have a ton of potential, still an active area of research, both in terms of things you can do with it and in terms of the actual GAN itself and how we stabilize it and how we kind of make it give us better results and do what we want it to do. And to end that, I want to show you a very, slightly trippy video, but just beautiful results that they got here from morphing different faces. And this is with that GAN model we talked about. And this is kind of what sells people on GANs, is there are a lot of optimization issues we talked about, but in terms of takeaway message, you can do really cool things with them. So like the resolution is actually like incredible in the real images. They do LSUN as well. I don't know 100% about everything else that's in here, but just completely new images, very high quality, all morphed into each other. And that's what GANs do for you. And I think with that, it's 3 minutes over, but we're pretty good. Any questions? All good?
Thank you.
All right.